So this, a good example of this is something where we can look at what I'll call first-order reaction kinetics. First-order reaction kinetics is that par C par T is simply related to some rate constant times the concentration of something. Okay? We do these experiments in chemistry, and they're very easy also to do in isotope space. The problem in isotope space is that you have to, as we'll see, you have to recall that it's an isotope ratio, and there's just a little extra mathematical thought that you need to do. Okay, so this gets into what you are, what you eat, part of my lecture. Okay, so carefully read the ingredients on everything that you, when you eat food. These are the cookies we used to eat when I was working in Pakistan. Sadly, can no longer go there. For me, about 20 years ago, I had a great opportunity to go to Mongolia. And this was the first National Science Foundation, National Science Council of Mongolia sponsored trip. And it's, one of those things that, again, is a piece of advice I can give to you. If somebody ever says to you, and you're listening in the audience, does anybody want to go? You just raise your hand. And this happened to me. Does anybody want to go to Mongolia? Yes, I want to go to Mongolia. So the plan was we were going to fly into Ulaanbaatar, and then we're going to drive up to Bulgan, where there's this huge earthquake in 1917, the magnitude like 8.8, and drive up to Lake Hoopsagul and see if we can core the lake, and then down here, back through Chesterleg, which is near the original capital of Genghis Khan, and back to Ulaanbaatar, wrap up meetings, go home. So I thought to myself, this is a great opportunity to see about diet change and how it shows up in humans. Okay, so I thought I'll sacrifice my body to science, and I will shave my beard every day. Okay, I have to actually shave. This is a tough thing. Last time I was fully shaved was when I visited my draft board in 1971, asking for an extension so I wouldn't have to get drafted and go to Vietnam. So, Mongolia is a high latitude, and we were going to North Mongolia, not South Mongolia. There are no C4 plants in northern Mongolia. These are grasses, but C3 grasses. These are horses. And when you're in Mongolia, you get the opportunity, as always, I figure wherever I am, whatever the locals eat, I will eat. Okay? So they milk horses there, which was a nice discovery. They drink horses' milk. They make horses' milk beer. So those of you beer aficionados, you want horses' milk beer, this is the place. If you like harder stuff, they distill it and make it into vodka. So horses' milk vodka. If you're interested, it tastes like jet plane fuel. And if you haven't had that, just try the stuff out of your car. It tastes about the same. So this is the history of my beard. I went camping in the Uinta Mountains with my family beforehand and noticed how there's a lot of change every single day. So I shaved my beard, collected my beard shavings, then flew to Ulaanbaatar, and there's actually this delay time. There's about a 5-day delay time, and then I'm in Ulaanbaatar eating at the same restaurant every day, out in the field, eating something slightly different, drinking this horse's milk stuff, and back to Ulaanbaatar, and then back on an airplane. And I distinctly remember that we flew from Ulaanbaatar to Tokyo, and out of Narita Airport on the Delta flight, they actually had corn chips. They rarely give you corn chips, but they had corn chips. And I thought, well, I see this in my beard, and apparently I did. Okay? So there's a time history in things. So let's look at the mass transport equation. There's all of this stuff, okay? We're not going to need most of it, but there are other times when actually all elements of these equations are needed to describe this time dimension. And just reminder here, Calvin and Hobbes, okay, all of this argument, I don't need math, and what are you going to be when you grow up? Every job requires some math. That's not true. I'll be a geologist. And he says, it's not really a job. So, okay, so no math. All right. One of the earliest experiments on the turnover of biological tissues was Keith Hobson, who teaches over in the class, and he did these experiments. What you do is you change the diet, measure the D13 over time, and then you do an exponential fit. Okay, this is really convenient because it looks kind of an exponential fit. Okay, and this is what it looks like. Okay, so good exponential fits, high R squared, everything looks fine. Have really short half-life for quail liver, slightly longer for blood, even longer for muscle, and really, really long for collagen. And here's the diet here. You're going to the corn diet, and so on. So this is just change the diet over time. All right. Now, Larry Thiessen had earlier pointed out that the exponential fit has some important elements in it. The final, this value of C for the exponential equation actually is the predicted final delta C13 of the equation. Okay? And the initial is just the difference between A and C, and B is related to the half-life. So we've got all these elements there. Now, one thing when you have a correct mathematical equation is to check how it works. Are things working okay? Okay? And what we see with Larry's with Keith's experiment is things look pretty good, but there's some subtle differences here. Okay? Delta I observed for collagen, he didn't actually get the correct initial value. The other ones, he got the correct initial value. That looks pretty good. So where this intercept is, it actually intercepts with the value it should be at 0. Okay? If it doesn't do that, there's actually information there. Where it really doesn't fit is the final value never fit really very well for anything, because the initial value should be the same as the final value. There's no physiological reason why the isotope separation should actually be a function of the initial stuff. So this is telling you important information. You got a pretty good fit, but there's more information. So you can do two things. One, you can give up and say, well, that's good enough, and that's okay. Sometimes you can't do more. But other times, what I want to explore is, let's just see if we can get more information out of these kind of experiments. Okay? So now I want to look at the first order rate constant notion. Okay? We have to do this a lot in our geological classes, and this is just the math thing. Okay, first order rate constant is this expression. The change in n over t is minus lambda n. Okay? So this is the exponential form of the equation. Okay, but one of the important, so that's what it looks like, and you could fit an exponential that, it'd really get a high R squared. Now, just looking at the data, this is a different way of looking at the data. We can look at a natural log space. In a natural log space, you can see this is a straight line, and one of the great things about straight lines is you can tell if they're straight, okay? And you can say, yes, that fits all the data really well. So now I'll give you two more sets of data. Okay, here's two more sets of synthetic data. And I've given you something that is the first set of data. And here's a slightly different situation. 10% of the stuff, whatever it is, has a half-life of 2 days, and 90% has a half-life of 100 days. And the line, I mean, as far as you can tell, that's just a good exponential fit, right? I mean, it really looks like a nice exponential line. But if we put this in the semi-log space, wow, things are really different. Okay, these two lines, they're significantly different, and this long half-life does not intercept 0. Okay, so if things don't intercept 0, it's telling you some really important fundamental information. Okay, so now we would like to explore this and back this out. And here's where it also becomes really useful in, well, all right. This is just for your notes, okay? If you want more details on this, just look at this stuff in your notes. But now let's put it into some space that we can use. And after we did our experiments, started looking into literature, and what we discovered is that people got discouraged because they would take a log of a negative number, and you can't do that, and so you go away. So you need to recast your space, and the dimension really is from your initial value, whatever that is, to your final value. Okay? And this is the new way of thinking about it. So you think in ratio space rather than delta space. Okay? And that's actually an easy thing to do. And now we can see that in our ratio space, this is the same as n is n0 e to the minus lambda t, just like that. All right, and we can follow this through. We called it the reaction progress variable. And here is a useful way to think about experiments, kind of what we like to do certainly in geology, and I'd like you to think about doing that in your own experiments, is we try to approach a reaction from two different directions. Okay, we start low, go high, start high, go low. Okay? So here's an experiment where this is just a synthetic experiment, and I've inserted noise into the experiment. Okay, so this is all synthetic data, but we've put in the sort of random noise that you would expect to get in your measurements. And importantly, so we've got two pools, a 20-day, 2-day pool, a 20-day pool, and we go high to a middle value, low to this middle value. We approach it from two directions. If we cast this in the semi-log space, what's really nice about this is we can use data from both experiments plotted together. So we can actually we have more data when we're trying to actually fit our lines. And this is extremely important if you're working with biological systems where you may be restricted in how often you can sample things. Okay, again, I'm a geologist. We can whack rocks. It doesn't hurt them, and they don't care. And then when we were doing these experiments with Denise, she says, oh, we'll just eye bleed the rats. I thought, what? Eye bleed the rats? Get your students to eye bleed the rats. I'm not going to eye bleed any rats. But you can only eye bleed the rats like every 10 days. Well, so you have to get a different rat to do day number 2 and a different rat to get day number 4. Okay, so if you're dealing with these biological things, it would be really nice to be able to combine all of your observations. And then notice here, we have data going in two directions. Okay, so these lines we have to fit only with the data from that particular experiment. But these lines down here, we can actually fit with both experiments. So that's actually very convenient. I'll show you another example of that in real life in a little bit. Okay, so this is the notion of our first order reaction kinetics. Okay, and now I'll just pause for just a quick time for any questions.